Okay, welcome back. Well, let's continue chapter 5. We talked a little bit about endothermic and exothermic reactions. We said that endothermic reactions take in heat, exothermic reactions give off heat. Well, qualitatively that's true, but sometimes in chemistry we like to do things in a quantitative manner. In other words, how much heat does this reaction give off, or how much heat does this reaction take in? So how am I going to measure that? Well, the way that we measure the amount of heat a reaction takes in or gives off is done by something called calorimetry. So what exactly is calorimetry? How does it work? And what do they look like anyway? Well, there's there's different types of calorimeters out there, but they're basically hybrids of these two. So let's talk about the coffee cup calorimeter. So what is a coffee cup calorimeter? Do we mean a coffee cup calorimeter? Well, technically I could make one out of this, I suppose, but that's usually not what we mean. In a coffee cup calorimeter, it usually looks a little something like maybe this. So you have something that looks like this. You've got, the reason they call it a coffee cup calorimeter is you have these two little styrofoam cups. You can do one or you can do two. You can get as fancy as you want here, I suppose. But what the styrofoam is there for is the styrofoam doesn't absorb heat and it doesn't release heat. Do you remember we were talking about system versus surroundings? And we said that the more you can narrow down your surroundings, the easier it is to do the calculations. Well, that's what the styrofoam is there for. It's to keep everything in, so you have less things that you have to worry about. So you got your styrofoam here, which is a good insulator. Not perfect, but pretty darn good. You can put a cover over here over the top if you want to. And then what we do is we put some water in here. Okay. You've got a thermometer that goes down here. You've got a little wire loop which acts as a stirrer because you want all the temperature of the water here, you want to be even all the way through. You don't want like temperature gradients. So you want to make sure it stirs up really good. You could probably use your thermometer as a stir if you're really, really careful, but you could use a metal thing here. All right. And so there's a couple of things you can do in a coffee cup calorimeter here. Is you could put a metal down in there, a hot piece of metal, and let the temperature of the water go up and measure the temperature of the water. And from that you can measure the specific heat of the metal. So that's one thing you could do. Another thing you could do with a coffee cup calorimeter is you could do what's called a heat of solution. You can take, remember when you put some salts, like for example the ammonium nitrate we talked about, you put some salts in water, it tends to cool off, or sometimes you put salts in water and the water actually heats up. And so what you can do is you can add a certain amount in there, you can see how much the temperature of the water goes up, and then from there you can determine the delta H, or what we call a heat of solution, for that salt dissolving. Okay? Or you can do a chemical reaction down there underneath the water, whatever you want to do. And that's kind of how your coffee cup calorimeter works. All right. Now, what's so nifty about a coffee cup calorimeter? Well, all calorimetry kind of has this in common. When you do calorimetry, let's say, for example, my reaction is exothermic. Let's say it gives off heat. All right. So if my reaction gives off, let's say, just throw a number out there, 50 joules of heat. Okay. What's going to happen to that 50 joules of heat? Well, heat can either be created or destroyed. Energy can't be created or destroyed. So if my reaction is giving off 50 joules of heat, it's got to go somewhere. So where is it going to go? Well, in a coffee cup calorimeter, my styrofoam here is a good insulator, so it's not going to absorb heat. It's not going to give off heat. Okay, my thermometer here, it's negligible. It's made of glass, not a lot there. Where is pretty much most of the heat going to go? Well, it's going to go into the water. See? So if my reaction loses 50 joules of heat, then that means my water has to what? Well, it has to gain 50 joules of heat. What if I have a reaction that picks up 100 joules of heat? Well, I can't just create that from anywhere, so where's it got to come from? Well, it has to come from the water. So if my reaction gains 100 joules of heat, my water has to lose 100 joules of heat. See? And that's just conservation of energy. That's what it is, really. So all that being said, what that means is in a coffee cup calorimeter, delta H for the reaction, because remember that's Q at constant pressure, and we're just doing this in a normal coffee cup, so it's 1 atmosphere pressure, is equal to negative Q for the water. Now, does that mean always negative? No. Negative here means opposite of. If this gains heat, this loses heat. If this loses heat, this gains heat. That's what the negative means. Okay? All right. So, if I want to know delta H for the reaction, how do I figure that out? Well, I look at how the system is affecting the surroundings, which in this case is my water. See? And that's why we're using styrofoam here, is we want to kind of narrow that down as much as we can. Makes the calculations a lot simpler. So how do I figure out Q for the water? Well, that's where that basic equation for heat flow comes in that we talked about in the last video. I know that Q for the water is equal to C for the water times M for the water times delta T for the water. So therefore, delta H for the reaction is equal to negative, parentheses, C times M times delta T for the water. All right, do you see what we're doing here? What we're doing in calorimetry is instead of measuring the amount of heat in the particular reaction directly, what you're doing is you're actually measuring it kind of indirectly. You're measuring how the reaction affects the surroundings, and once you know how it affects the surroundings, now you can correlate that back to how the system works. Make sense? So it's kind of an indirect way, really, of measuring the amount of heat in a chemical reaction, or whatever process you happen to be doing. All right. So problem time here. Suppose heat from a reaction is absorbed by 412 grams of water, raising its temperature from 20.12 degrees Celsius up to 29.86 degrees Celsius. What is delta H for the reaction? Okay, well, I know that delta H is equal to the negative of 4.18 joules per gram degree Celsius, because that is the specific heat of water. Talked about that, I believe, earlier. Takes 4.18 joules of heat to raise 1 gram of water 1 degree Celsius. Okay, that would be given to you on a test. That's not a number you have to memorize. How much water do I have? Well, I got 412 grams of water. Okay, raising its temperature from 20.12 to 29.86. Okay, so what's delta T? Well, remember, anytime you see a delta, that means final minus initial. So where's my final temperature? Well, it's that 29.86. What's my initial temperature? 20.12. And so, oh yeah, it should be a 2 there. I've got a 9 there for some reason, but it should be a 2. 20.12. All right, final minus initial. By the way, if you've had calculus, and if you haven't had calculus, you could ignore what I'm about to say. Anytime you see a delta in front of something, replace that with a little d, a differential. There's your calculus-based thermodynamics right there. Okay? If you haven't had calculus, just forget what I said. Doesn't matter. Final minus initial. Okay? All right. So we plug everything in. So we say 4.18 times 412 times whatever 29.86 minus 20.12 should be, and you get 16,774 joules. All right, so what that means is the water absorbed 16,774 joules of heat. Okay, now if the water absorbed 16,774 joules of heat, what had to have happened to the reaction? Well, it must have lost 16,774 joules of heat, because it's got to come from somewhere, right? And so, see, that's what this negative means. It just means opposite of. All right? Well, that's a big number. Is that a number you would tend to get normally in a chemical reaction? Sure, all the time, sometimes bigger. A joule is just a tiny little unit. It's just not a very big unit. It's like measuring distances in inches or millimeters. So typically, when we do delta H's, we typically tend to measure heat given off or taken in on the kilojoule level. So what we do is we convert that to kilojoules. So we're going to find our decimal here, where it is. We're going to divide by 1,000 or move our decimal 1, 2, 3 places back, And so we get negative 16.774 kilojoules. And that's delta H for that chemical reaction. Is that endothermic or exothermic? What's exothermic, because delta H is negative, does this reaction give off heat or take in heat? It gives off heat, negative delta H, exothermic, heat going out. One way you could look at it. All right, and that's exactly how much heat went out. Do you see what we did is we measured the heat from the reaction by measuring what happened to the water, and then indirectly kind of correlating that back to what we measured what's happening with our system by looking at our surroundings. And that's how calorimetry works. And really, when you're doing calorimetry, you know, the tendency here is for students to try to memorize equations. You know, I get it, but really, when you're doing calorimetry, don't think of it in terms of memorizing equations. Think of it in terms of, okay, where is this heat going? Can I calculate how that's affecting this over here? And then whatever's happening in the reaction is the exact opposite of that. Because if this is gaining heat, this is losing heat. If this is losing heat, this is gaining heat. Okay? And the nifty thing about a coffee cup calorimeter is you've narrowed your surroundings down so much that it's a very simple calculation. The only thing affected here would be the temperature of the water. And so that's where this is, right here. Make sense? Okay. What is the downside to a coffee cup calorimeter? Well, the downside is styrofoam a perfect insulator? Well, it's very, very good, but it's not absolutely perfect. The other problem is, let's say, for example, maybe I've got gasoline. Maybe I want to know how much energy is in 10 grams of gasoline. Do you think burning that in a coffee cup calorimeter would be a good idea? Well, why not? Well, yeah, I mean, you blow that little coffee cup calorimeter to bits. You know, that styrofoam start melting. Probably as soon as you pour the gasoline in, it'd probably start dissolving in the gasoline. So, you know, for a teaching tool, it's great. It's cheap. But it's probably, if you're trying to do serious research, you know, a styrofoam cup is probably not the way to go. So, you know, how do I do actual serious research in calorimetry? Well, that's where something called a bomb calorimeter comes into play. All right, so what's different about a bomb calorimeter? Well, see if I can find you a nice picture here of a bomb calorimeter. Ah, here we go. Okay, so this is a little bit more serious research equipment here. Okay, looks like this. It's going to cost you a little bit more money. So how is a bomb calorimeter constructed? Well, with a bomb calorimeter, now you're talking all stainless steel. You know, no more styrofoam. We got to have something that's durable here. So you've got a stainless steel tank here, which quite often holds some water. You've got this part in here, which is made of metal as well. Okay, and then inside that you have a thermometer here, which is highly precise. So we're talking about tenths or hundredths of a degree instead of 1 degree thermometer. So a precision thermometer. You've got a stainless steel cylinder in here, which usually has some sort of a screw top with a gasket, and that is called the bomb in your bomb calorimeter. Okay, and then inside that you have a sample cup. Okay, and essentially what you're going to do is you're going to light this thing up. Let's say for example I'm dealing with natural gas, and so I pressurize my bomb here with the natural gas. Well, the problem is how do I light it up? Every time I try to stick the match in there and it goes underneath the water, it goes out, right? Well, what you've got is this platinum wire here, really thin platinum wire that goes to electrodes, which goes out here to a battery. Okay, and so what you do is you hit it with a spark, and what that does is that lights up your sample in here, and you actually have an oxygen inlet here because you obviously can't get it to burn without oxygen. And sometimes you get kind of an explosion. I mean, there's a boom there because it's it's kind of in a really rigid cylinder there, and so yeah, that's why I call it a bomb calorimeter. and then your reaction happens inside that. If that's the case, where does the heat, let's say it's an endothermic or an exothermic reaction. So if that's the case, where does my heat go in a bomb calorimeter? Well, some of that heat goes into heating up the little sample cup here. Okay. If I have water inside the bomb, sometimes you, when you're doing nitrogen analysis on foods, things like that, most nitrates are soluble, and so yeah, you put that in the water here, and then you can take the water out and do a titration and figure out how much nitrogen. Sure. By the way, why would you care how much nitrogen was in food? Where would your nitrogen mainly come from? Yeah, proteins, amino acids. Yeah, so it's a way to determine how much protein is in some food there. So yeah, that's where food chemistry kind of comes into play. But yeah, it's going to heat up the sample cup here, which is made of metal. It's going to heat up this bomb here, which is made of metal as well. It's going to heat up the water in the bomb calorimeter. Okay, it's going to heat up the stirrer here, this little mechanical stirrer that you usually have to kind of keep the water nice and constant. It's going to heat up the thermometer. It's going to heat up this wire that's coming down here. Your tank's made of steel, so it's going to heat up that as well. So how do I calculate this? Well, I got to find, the heat capacity of the cup. I got to figure out C times M times T for this. I got to figure out C times M times T times for this. I got the stir, got the water. Man, that's a complicated calculation, right? Well, here's the thing. Let's say, for example, you and I are making bomb calorimeters. We're in competition with each other. Do you see that if I can somehow make my bomb calorimeter easier to use than you can make yours, I'm going to sell a lot more bomb calorimeters. Because what people want is they want like a big box with a button on it that they can push, and out pops the answer. Kind of like CSI. It used to irritate me when that show was on because, they'd run something through a computer and up would come like a picture of the molecule, like a screensaver, and it would rotate in 3 dimensions and, the names underneath. Doesn't work that way. Only works that way on TV. Okay. But yeah, I would love to have an instrument that worked that way. All right. So here's how they make your life a little easier. In a bomb calorimeter, where does the heat go? Well, there's 2 places it kind of goes. Okay. Your heat goes into the calorimeter itself, which is made of metal, and I can't assume that it doesn't absorb anything because it's made of metal. This is not styrofoam anymore. Okay. It's going to heat up. And it also goes into the water that's in your calorimeter there as well. Okay. So how do I figure out how much heat goes into the calorimeter? Well, think of it this way. The tank that I'm using is always the same tank. The bomb that I'm using is always the same bomb. I'm always using the same wire. I'm always using the same stir, and so on and so forth. So instead of calculating C times M times delta T for every single one of those pieces every single time, what I can do is I can calculate a big giant C for the entire calorimeter. And this is called the calorimeter constant. Okay? And basically what it is, it's all those little C times M times delta T's all rolled into one big giant number. All right? And so essentially what they do is at the factory, they take a certain reaction that they know gives off a certain amount of heat, and they run it through the calorimeter, and they see how much the temperature goes up, and they calculate the calorimeter constant, okay, which is what this big C is. Every calorimeter is built differently, so every calorimeter has its own calorimeter constant, but that's usually stamped on the bottom of the tank or, in the literature or something like that, and so you don't have to do those calculations all the time. So this is how much heat goes into the calorimeter. The calorimeter constant times the change in temperature. Okay, so how do I figure out how much heat goes into the water? Well, that's just C for the water times M for the water times delta T for the water. Add those together, that's how much the entire bomb calorimeter absorbs. The opposite of that is how much heat the reaction either gains or loses. See? All you're doing, and again, you can memorize equations, but really it's not the best way to go in calorimetry. The best way to go in calorimetry is say, okay, I got a reaction that gives off heat, where's it going? Well, some of it's going here into the calorimeter. how do I figure out how much is going there? Well, that's this equation right here. Some of it is going into the water. How do I figure that out? Oh, well, that's this equation right here. See? So we add those together, and then the opposite of, again, that's what the negative means. If this is gaining, this must be losing, and vice versa. There's your Q for the reaction. You're measuring Q for your reaction by looking and seeing how it's affecting the surroundings. Okay, so if you logically go through that instead of trying to memorize this one big long equation, you understand what, how, and why. It's always better to understand how and why instead of just how. Okay? All right, well, I'm assuming you want to do a problem, so let's do a problem. All right, so suppose the combustion of 1.6 grams of methane, that's CH4, that's just natural gas, in a bomb calorimeter containing 45.6 grams of water raises the temperature by 5.14 degrees Celsius. What is Q for the reaction? And I will give you that C for the calorimeter here is 17.2 kilojoules per degree Celsius. In other words, it takes 17.2 kilojoules of heat to raise that entire calorimeter up 1 degree. All right? Okay, well, I know that Q for the reaction here is equal to negative Q for the calorimeter plus Q for the water. So how do I figure out Q for the calorimeter? Well, that's calorimeter constant, 17.2 kilojoules per degree Celsius, times the temperature went up by 5.14. Is that going to be positive 5.14 or negative 5.14? Well, it's going to be positive because my temperature went up, it didn't go down, right? So times 5.14 degrees Celsius. Okay, so this tells me how much heat the calorimeter absorbed. How do I figure out how much heat the water absorbed? Let's just see for the water, which is 4.18 joules per gram degree Celsius, again, constant, be given to you, times the mass of the water, 45.6, times 5.14, positive, because it went up as well there, and there is Q for the water. Add them both together. The negative of that is Q for the reaction. See? Instead of looking at the big long thing, think of it in terms of pieces. Here's Q for the calorimeter. Here's Q for the water. You just added them together. 17.2 times 5.14, 88.4 kilojoules. Okay, 4.18 times 45.6 times 5.14. You can check my math on that, but I believe that's 979.7 joules. Okay. Be careful here. All right, and it just kind of depends. Some books like to do this, some books don't. But some books just feel the need to make the problem harder for some reason. And you'll notice they gave you the calorimeter constant here in kilojoules per degree Celsius. And the specific heat of the water here is in joules per gram degree Celsius. This answer is going to be in kilojoules. This answer is going to be in joules. Can I just add those two numbers together? No, I can't add kilojoules and joules. I need to get them both in the same units. You could either convert this to joules and then add it to these joules, or you can convert this to kilojoules and add it to these kilojoules. But you can't add kilojoules to joules. All right, now sometimes they'll give you the calorimeter constant in joules per degree Celsius. And if that's the case, this answer will be in joules. Just add them together. It's no problem. But sometimes they'll get tricky on you. They'll try to do this. So if they do, watch out for it. If they don't, then, you're okay. But be careful. Okay? Now, in my opinion, it's probably better to convert everything to kilojoules. Because remember, when we calculate heats of reactions and things like that, we normally express those in kilojoules. So I would probably convert this to kilojoules. So we're going to move our decimal 1, 2, 3 places. So 979 joules is 0.9797 kilojoules. So 88.4 plus 9.979, negative, and then negative here, 89.4 kilojoules. If my calorimeter absorbed 89.4 kilojoules, that means my reaction must have given off 89.4 kilojoules, hence the negative. Make sense? And so I can do a lot more rigorous, dangerous reactions in a bomb calorimeter, and I can do things a lot more precisely in a bomb calorimeter. This is your research quality stuff. But the calculations are more complicated because you have more stuff to deal with. All right, but the calorimeter constant at least makes it easier because you're not having to figure out C times M times delta T for this little part and C times M times delta T for that little part and all these little parts and add them together. They just take most of those parts except for the water and just roll it into one big giant constant because you're always using the same bomb, you're always using the same tank, you're always using the same stir, and so you can get away with that. And it just makes the calculations easier for you. And that's why they do that at the factory. This is usually experimentally determined. So again, this would be given to you, on a test. Okay? All right, and those are the main two types of calorimetry that you run into. Okay, let's talk a little bit about thermochemical equations then. What's the difference between a regular chemical equation and a thermochemical equation? Well, the main difference is there's one more piece of information. You specify the delta H in kilojoules. So a regular balanced equation would be something like this. H2 plus Cl2 goes to 2HCl. All right. What makes this a thermochemical equation? Well, the fact that we're giving the delta H here. Delta H is equal to negative 185 kilojoules. Okay. What does this equation mean? Well, this means that when I form 2 moles of HCl, 185 kilojoules of heat is it given off or taken in? It's given off because of the negative here. Okay? So 1 mole of H2 will react with 1 mole of Cl2 to form 2 moles of HCl, and 185 kilojoules of heat is given off. So see, it's a regular equation with just one more piece of information. Okay? This is mercury oxide. 2 mercury oxides will go to 2Hg, 2 mercuries, liquid mercury, plus O2, and delta H for this is positive 182 kilojoules. Okay, is this endothermic or exothermic? That's an endothermic reaction, positive delta H. Okay, and what that means is if I want to decompose 2 moles of mercury oxide into 2 moles of liquid mercury and 1 mole of oxygen, I have to add 182 kilojoules of heat. All right, so see, it's like a regular chemical equation. It's just with one more piece of information added, and that's the amount of heat either given off or taken in. Make sense? Okay. Well, what that leads us into is the 3 rules of thermochemistry. Are these the 3 rules of thermochemistry? Well, no. They are the 3 rules that we're going to talk about. Okay, but they're not like the, first and second and third law of thermodynamics or anything like that. But that's what we're going to talk about in the next videos. We'll talk about the 3 rules of thermochemistry and how to use those. And we'll go from there. So, making progress. I guess I'll see you in the next video. So, bye for now.